Is it possible to switch between the current topic and the open topic?
You may negotiate.
I want the G09 software.
But it's all about G09.
No, this one.
Symmetry. Okay.
And what about share experience on the Gaussian C class?
We can add it. If you want number 9, we just add it to cover the
Both of them?
Oh, yeah.
Oh no, very
Come on, this is very easy. So,
how much time do you have? Similar to the previous one?
yes. We have more visitors. You have seen that there are many slides, but some of them are repetition and review of what we did before. So, in some sense, this meeting is the main one in the chapter. So we are focusing on the electronic degrees of freedom, and we assume that ions are nuclei are nailed down, and we look only on the atomic structure. The last night in the lab, you practiced analyzing energies of molecular orbitals, and you already know that there is an output in the software that gives the total energy, which is philosophically the main goal. Find total energy of a molecule. Orbitals are auxiliary concepts, but they really help you in analyzing properties of materials. And you were also drawing molecular orbitals. We do have all background information to actually do Hartree-Fock theory today. All other things were building blocks, and now we can put them together in a real house. This is a plan from last year, and we will, do not worry, presentations are not on Tuesday, they will be on Thursday. And on Tuesday we will do Ostlund's theorem, which is a little decoration that helps how to interpret. So I will discuss and summarize what we're doing in a lay language, and then we'll go through the details. There are 3 types of outcome from Hartree-Fock theory: total energy, orbitals, energy, and orbitals as distributions in space. We have all concepts that help us to get them, like anti-symmetry, variation principle, but we need to look at actual equations that are being solved in the brain of the computer. You already got the idea that wave function of this modular system is composed as antisymmetric product of molecular orbitals, and molecular orbitals are composed as superpositions of atomic orbitals, like hydrogen S and D orbitals. And we also got the one electron fork, which was showing the equation that has traces of mean field of interaction of one electron with background propulsion from other orbitals. But these equations were cast in the abstract form for 3-dimensional distributions of this one electron. These 3-dimensional shapes that we draw as orbitals are still not very comfortable for computer process. There are several standard procedures for which one has very quick optimized Szabo times, can be parallelized, and the goal of a programmer is to reduce whatever mathematical problem to one of the standard algorithms, like a search, steepest descent, and dimensional surface, or diagonalizing a matrix. well, there are also propagation differential equations, but in some sense, there are a limited amount of solvable numerical problems. And we are going to recast one electron Fock equation in a basis of atomic orbitals. If you do this, if you recast it in a basis of atomic orbitals, you will avoid these three-dimensional shapes, which are still, they're doable today with the computer, but they're not comfortable. And instead of these three-dimensional distributions, as you see all of the orbitals, in actual calculations, computer deals with expansion coefficients, with which percentage, with which proportion atomic orbital enters into specific molecular orbital. And if we convert everything we did into the language of this linear combination coefficients, we will use letter C. Then it will be actual equations that are being solved. So instead of wave functions, we need numbers, expansion coefficients, which we will save in the form of vectors. And equations that are being solved will be formulated as diagonalizing matrices. You can formulate a matrix, formulate a vector of expansion coefficients, and then to analyze how it is connected to what we were talking before. Any objections on this idea? So you've got some differential equations. You are fine with the concept of basis functions and representing any function and expanding the basis, right? And you will take it as it goes.
So it's not the analytical solution, right?
It's
numerical.
Numerical solution. Numerical solution, and it will be iterative because I will explain it later. It's important but secondary. This diagonalization will be repeated in a cycle Y, same as you were optimization.
You mean the basis function should be fit to the answer, or
Not basis functions. Basis functions are once and forever, but expansion coefficients can be fit.
okay, yeah,
Okay.
there is constants in the series. So.
Right, and you can tweak this concept until you get the right solution. Good?
This expansion coefficient we are getting from Eigenstates.
Right, exactly. Yes. So basically, you got the idea, and I will return to it several times. These are shorter summary slide, and then with all derivations. Derivations are not our goal, but I will feel mandated to show, even if you don't care. So what will be the main step in the derivation? So we already have equation for this analytical continually distributed functions, and we need to get expansion coefficients. In order to get rid of wave function, one needs to apply orthogonality property. Because if one multiply wave function with another wave function and integrate, they will convert into a delta function. We already did it when we were going over Born entangler approximation. Remember? Maybe you remember. But this is a standard trick in deriving equations, and we will practice it again. We need to get from analytical to matrix form equations, discrete form, and we will use orthogonality property. So this is how you were voting. Is now I will replace open matrix and make a little bracket. I'm going to show a little bit more chance to show this trends. So we are going to get two summary slides at the end of the meeting if you will survive. If I survive presenting this material. So those, and we will go careful about the meaning of each symbol. So this C vector is the column of expansion coefficients for a molecular orbital number I. F is one electron Fock operator which replaces Hamiltonian as traces of electron-electron interaction. E sub I are energies of molecular orbitals that you are already analyzing in homework and using for density of states. Okay. So this is a waste of energy because eigenstate equations have many solutions. This is again unknown vector that we need to solve, and S is overlap matrix because the atomic basis is not always orthogonal. So we have to fit whatever. And as in linear algebra, if one needs to solve such equation, one moves everything to one side, removes unknown vector, and finds determinant of matrix, right? So if you agree with this writing, basically you work. The rest will be technical details. Another thing that one starts with positions, with draw model. Then in order to launch, one needs some even arbitrary expansion coefficients. And then these arbitrary coefficients one formulates Fock methods for this diagonalization, makes diagonalization, and computes, so one box listed here, computes total energy. And computes new expansion coefficients. Then expansion coefficients are used to reformulate Fock methods, solve through diagonalization, and compute energy once again. So if the total energy at each step of this cycle will converge to a small, with less and less deviation, the change will be under some tolerance limit, it's considered that it's converged, and one can go to compute observables, orbitals that analyze gaps, both orbitals and some other things. Why, where this cycle comes from, why it is needed? One helps from linear eigenvalue problem is a linear procedure. You solve it and you get answers. Although it is like set of eigenvectors and eigenvalues, you just do it at once. And there is no ambiguity. There are so many solutions, but they are in some sense deterministic. But it is one electron problem. And the force, the potential of interacting with the rest of electrons is nonlinear. So in some sense, we are solving nonlinear problem of many electrons. And if when we do it once, expansion coefficients will be different, and force acting on electrons will be different. And this, in some, we are solving nonlinear problem. There is no standard algorithm for diagonalizing nonlinear problems. So one needs to do this optimization-like cycle, or people call it self-consistent. So until forces between electrons and energies will become agreeing to each other, will be consistent, independent of how many times we cycle, then solution is approximate solution has been found. If you hate this nonlinear problem, then you are welcome to solve true multi-electron problem, which will be your number 10 to the 42 for small, etc. and more. It will be several of orders of magnitude more complexity, so it is a reasonable price to solve nonlinear instead of linear to access quicker, substantially quicker solution. So this is the end of the Hartree-Fock theory.
And usually the result should be an average from different rounds with independent initial configuration or no. For instance, made this model be trapped in a local minimum of optimization or no.
It happens. And the many pieces of software like Gaussian start telling that this electronic structure for this model cannot be converged. Probably it's a bad model.
So maybe, for instance, for each round, if you have a randomized initial configuration, each round may give you a different minimum. If you trapped in a local minimum. For instance, in molecular journal, people try to do round 5 simulation and get the average with the error bar for the results. So
you are setting up a very strong question, which is a central question of modern computational chemistry. Hartree-Fock theory is designed in like almost 100 years ago, 80 years ago. But you taught very important word, configuration. So you probably were projecting an analogy with molecular nuclear configuration. And here we are coming to electronic configurations.
Configuration is the same. We want to minimize the maybe potential energy surface.
Exactly, potential energy surface, but before our nucleus are now fixed. We do not change nucleus. We are browsed in the space. Instead of coordinates, we have expansion coefficient. Quite abstract. But all Hartree-Fock theory uses concept of Slater determinant, and it rests on the assumption that there is only one Slater determinant at one time. But it is not necessarily. If there are some electronic configurations, so-called triplets, when there are coexisting three determinants, and for them, like you do numerical experiment, your Gaussian software panics, tells you gave me wrong problem, it has no solution. I'm frustrated. Stop. And in the drop-down menu, you have several methods, and you just get more higher order methods that will not panic and solve the problem, maybe for like 100 times longer investment of computer resources. So molecular Schrödinger equation with all degrees of freedom does not have ambiguities. It is it is always solved. But this approximate methods can't get stuck. You are very correct in asking that.
So the Hartree-Fock theory only uses the repulsion of the electron and electronic cloud.
And exchange interaction.
Exchange interaction.
So it is a good theory, but it neglects multi-determinant nature of that is often happens for unpaired spin for excited states. So it's a good starting point if you really need to model something advanced.
It is just like you showed us. It calculating the energy, just taking the one electron outside and putting them back and forth and taking the other electron as a function of how to say. I don't know the word. Superposition.
Okay. So I'll probably we do not have time for review. I'll just quickly skim through. Slater determinant, function, one function variation principle. This is important. I was drawing it on the blackboard yesterday, and this is atomic expansion coefficients, and there is a set of s,p,d orbitals on each ion, centered on each ion. So we need to make summation over ion and over a set of quantum numbers. And then all of this, like set of quantum numbers of one ion, set of quantum numbers of another ion, set of another ion, and we add all of them together with this expansion coefficient. And for each molecular orbital, HOMO, and others, we will have index of this molecular orbital. But we want, instead of drawing molecular orbital, searching for molecular orbital as function of Cartesian coordinates, we want to solve equation for this C coefficients. This is something that we will use. And this molecular orbitals as function of Cartesian, it is what you were doing yesterday in the cube files. Long exchange. One of exchange. And now we actually start. So Hartree was it's Wikipedia version. So he was trying to address things about multi-electronic nature, and he decided that if there are many electrons, one has to separate variables and consider wave function of many electrons as a product of one electron. And he had an interesting career contributing to developing supercomputers. So he developed this idea of mean field theory and going over cycles. But after people started to practice this hypothesis, this theory, one was observing substantial deviation from experimental results. So it was a cool theory, but by some reason it was wrong. Hartree-Fock contributed an idea to take anti-symmetry concept into the Hartree methodology. So it was very little addition, like to long add exchange, basically. But then, since exchange has minus sign, it stabilizes. It predicts that most molecules will be stable, will have stable. And I was taking undergraduate class from the former graduate student of Fock. So just half a year before he passed away. So there was a little connection. I didn't understand much of it, but it was a little encouraging. So we are going to work on this extension coefficients. So Raju, you originally elected to talk a little bit about base, and then I asked you to do it more. So basis set, to what we talked by now, it is a set of atomic orbitals. But atomic orbitals are very bad in mathematical sense. Why they are bad? The mathematical expression for S orbital, looks like I skip normalization. E to the power absolute value of position of electron minus position of electron. So if one draws this function, if you have a cusp, right? So exponential decreases if it goes to the left and to the right for the special point. And on this cusp, the derivative will be infinite. Right. Those non-analytical functions or discontinuity derivatives are a big pain for real calculations. And if one replaces this function by a function that looks almost the same way on the edges, and in the center is a little continuous shape, one will get very minimal error for any interatomic overlaps, but all overlaps, all multi-electron intervals, all matrix elements will be computed without problem. So why the software that you're practicing is called Gaussian? Yes. Because atomic orbitals are replaced by Gaussian functions. Okay, so it was a there is no philosophical discovery in this, but it was major, how to say, software engineering discovery. So as soon as people did it, one was able to. Before this trick, it was not possible to do anything. It was like.
If we use the Gaussian, it's gonna be the magnitude is gonna be double.
Well, one can expansion of arbitrary function in a certain basis is possible. Wait. Is possible if the basis is complete, right?
Yeah.
And if you replace one complete basis to another complete basis, the theorem will not suffer. We can represent the same function through any representation of a basis if the basis is complete. So in some sense, it doesn't matter which functions we use. There are mathematical theorems that one can, any complete basis will be sufficient to represent function. And we use our chemical scientific intuition because the basis functions in the software look like atomic orbitals, but they are not atomic orbitals. They are modified in order to be comfortable for certain mathematical procedures.
For this one, the basis function is reversal.
Yes. Yes. And let me continue with some little illustrations. So if we have the S function on the position R2 to the same function for the side, right? If we have P function R1, then it will be 0 with over this point, and then it will decrease. Right? So it is kind of one-dimensional representation of SP orbitals. And anywhere where we have E minus absolute value of distance, in Gaussian it will be square. And there are some additional tricks. And there is a big nomenclature. One can dedicate him or herself to the basis function for the whole life. And if you look through some drop-down menu, there will be like STO, like simple superposition of those orbitals. And then there will be nomenclature of 631G. And I do not want to waste our class over that time, but we can just bring how to open this nomenclature. Typically, the deeper in this drop-down menu you go, the more precise, more complete this set is, and more perfect the calculations will be. But this is a story about atomic centered bases, which was traditional approach for computational chemistry for like the whole 20th century, or maybe until last decade of the 20th century. One was thinking that computational chemistry is for like water molecule, benzene molecule, maybe aspirin, some molecule. But at some point, one decided like, what if we need solid states and nanostructures? And third, the main property of solid states is that they are infinite in a sense of micro-world. If you look on few atoms, there are repeating unit cells. And atomically centered basis functions are not ideal there. So in a week and a half from now, we'll start new software, new chapter, and we will focus on a different philosophy of basis. Right now, there is a theorem that function can be represented in a basis, in any complete basis. But we are using atomic-like functions centered on atoms. But no one forbids to use plane waves, like infinite periodically oscillating functions, same like in Fourier series, to represent molecular orbitals. And this is the most useful way for solid state, for nanostructures. And in a week and a half from now, we will focus our attention to it. Yeah, just show you how this is. So index of orbital and all atomic orbitals and index of the nuclei. So once again, V-Fock operator, kinetic energy of first electron, attraction of first electron to all nuclei, and then repulsion of the first electron from all but one electrons, and attraction to the rest of the electrons through exchange method. We do need to reformulate this abstract in what Ray described either in abstract space or in continuous discrete space. In a continuous space, we need to reformulate it in the discrete space of expansion functions. When you were doing a summary of today's lecture, expected outcome, you have seen the letter S. Right? If you look through this out, you will see this letter S on the equations 3.136. And the last equation on the last page, you see this eigenstate equation with this S symbol. So this discussion continues our view on basis functions. If we select basis functions as plane waves, as infinite exponentials, oscillating exponentials, or sines and cosines, then these sort of basis functions are orthogonal by definition to each other. Right? Oscillating functions of different frequencies are orthogonal to each other. It's a background of Fourier series. But atomic functions, they are orthogonal to each other only if they are on the same atom. But if you have two S functions on one atom and another atom, you multiply them, you integrate, and the result will be non-zero. So atomic orbitals originating from different atoms are not orthogonal. So we still have a complete basis set. But it is not, it is complete but not orthogonal. And this S, yes? We need to get rid of wave functions, atomic wave functions. Yes. We need orthogonal expansion conditions. In order to get rid of continuous functions, we need to practice orthogonality. We need to integrate another basis function, and then they disappear. There will be either delta function 0, 1, or matrix 7. And typically, if the basis set is good quantum basis, all basis functions are expected to be orthogonal. So if we have atomic function with one set of quantum numbers and atomic function with another set of quantum numbers, multiply, integrate, we get 0. If it is the same number, we'll get 1. But if these atomic functions are sitting in different atoms, they will be not orthogonal. It will be neither 0 nor 1. It will be something in the middle.
In different atoms?
Yes. So we need a measure. We need to quantify how much these atomic bases are not orthogonal. And this S object is a measure of this non-orthogonality. Let's say S orbital on one atom, P orbital on another one, and in this region they will be interacting and providing something between 0 and 1 on formula integration. So function 1, function 2, integration variable is the same, but they are evaluated at atom 1 and atom 2. So this S mu is degree of non-orthogonality of the basis functions. If you take calculation of sparse helium gas between stars, where all atoms are very far from each other, then this term can be neglected. But if it is something dense with chemical bonds, when atoms approach close to each other, the error associated with this non-orthogonality can be substantial. So one needs to foresee this feature and take care of it. You already know how to deal with volume exchange.
This is the reason for the carbon sp orbitalization.
Huh?
This is the reason of carbon sp orbital
hybridization. It is related to it. But hybridization is how these s and p orbitals come into hybridized, how they are superimposed in molecular orbitals.
They're saying that.
So this is what we have now. And in this equation, we want to get rid of the orbital as function of position. Yes. Okay. Now, if you were relaxing, leaning back, not focusing, it's fine. Let's focus briefly right now, and then you can relax further if you need. So we are going to use expansion of molecular orbital in basis of atomic orbitals. Let me draw this. And we are going to plug in this expansion instead of molecular orbital here and there. From now on, we will have no molecular orbitals, but only atomic orbitals and expansion coefficients. Right? And in order to keep expansion coefficients and delete atomic orbitals, we will need to practice orthogonality, or whatever we have instead. So we will need to multiply by another atomic orbital and integrate. If you want to object now, to stay silent forever.
Focus.
Huh?
Focus.
No, it's different thing. It's not focus. It's orthogonality. We are practicing orthogonality to get rid of atomic functions. Okay, I better write it to attract more attention. So we do have f, which is f. And here, instead of wave function, I'm summation of all quantum numbers. C, U, I, U. And I will die if I will write explicitly well, equals energies I summation U C U
This should carbon as R.
Yes. Now, I want to practice the following property. Integral of chi mu times chi u dr equals, it will be not delta function as we may want, but it will be s nu nu. Let's just assume that index of ion is stored in this big superindex U. Otherwise, it will be too many writings. So when we do have two wave functions, two atomic wave functions, we can convert them into this S matrix. And S matrix is not a function; it's a set of numbers in a matrix. We already have one wave function here and there, but we are missing another one. So in order to practice this idea, we need to write here integral dr I u star. And here we also need to put integral dr I u star. Okay? It's not forbidden to multiply both parts of the same. Now, the expansion coefficients, they are not operators, they are not functions. So one can put this expansion coefficients and this summation up front. Right? So we can swap the multipliers. So yes, with constant it is allowed. With quantum objects, not always. So let's put this stuff up front. And now we write what summation C u into dr star u for operator f I equals eigenenergy I integral dr star. No, wait. Exactly. Thank you. Summation. Then we put the R. Okay. You're proof. There were no dirty tricks. Everything is good. Now, we know that this combination can be replaced by this S matrix, right? And this combination is conversion of abstract operator into set of matrix elements, right? So for each value, for each set of coefficients mu, and for each set of coefficients nu, this will be one number. So instead of Fock operator, we will call it Fock matrix. M, U, and this one we'll call S, U. Right? So if you look onto the last line of last equation, it should be very similar to this. So summation C coefficient Fock matrix equals energy summation S matrix C coefficient. Okay. I'm going to do few more slides with wrapping it up in a more comfortable way, but basically you got the core of the Hartree-Fock theory. This is equation, if you formulate this Fock matrix and S matrix. This is equation that computers are trained to solve. There are standard several times that do it like that. So we need to, if suppose that we live on the inhabited island, we design our own computer, we want to write a Hartree-Fock theory equation. We can do only part of formulating this equation, because diagonalizing a matrix is a natural thing that anyone with computers will cover. We will utilize background created by other applied mathematicians and programmers. So, or it is the same thing, just typed. But I don't know, maybe you prefer nice typing. I think when someone writes, it's a little better. So we plug in the conjugated function to the left and to the right, and use that atomic functions are not orthogonal, but their orthogonality or non-orthogonality is stored in the form of this matrix. And by plugging it in, we are getting Fock matrix. One can also notate it in private applications. This, I don't know why you need so many slides, but you put the ideas, right? So summation, Fock matrix, expansion coefficients, S matrix, expansion coefficients. Now, if those are matrices and vectors, why do we use this summation, and why do we write so many indices? If you look on this equation, and you recognize this the same thing. Last 20 slides were just in this. So summation matrix, first index, second index, and then vector with another index. When these two indices coincide, it means row by column. So this can be considered as a column vector. Same here, row by column. This is vector, this is matrix. So you can represent these objects. And by the way, I want to give credit to Professor Roothaan, who has designed this conversion of Hartree-Fock abstract theory into equation that can be solved on the computer. And in the Wikipedia, it tells that he got his inspiration idea while sitting in the opera, listening to music. So if this set of expansion coefficients is a vector, so for each molecular orbital there is a set of individual atomic orbitals, and we write it as a vector, then in the same approach we can write this Fock matrix as a matrix, S matrix as a matrix, right? And then the Hartree-Fock Roothaan equation will look this way: matrix, vector, eigenvalue, matrix, vector. Right? If we would try to solve maybe H2 molecular hydrogen problem with a lot of painful effort, a human can do it. But it's much better to trust computer to solve these equations. And if one needs to diagonalize a matrix, you will have it from linear algebra. You subtract left and right, so that it will be each element here minus unknown eigenenergy and second matrix. And then this known matrix multiplied by unknown vector equals 0, which will be satisfied if the determinant of this matrix is 0. And then this determinant converts into polynomial, which you need to find roots. These roots will be follows. If I hate writing many indices, I can use bold symbol for matrix, vector symbol for vector, and then this will be the Hartree-Fock equation. And if one needs to find this eigenvalues, the determinant of this subtraction. That will give the set of molecular orbital eigenenergies we were using for the Eigenstates in the last step. And as we discussed at the beginning, this equation is solved in a cyclewise fashion again and again, because as soon as you find expansion coefficients, they are used backwards to reformulate for matrix, and one needs to repeat this procedure. Thank you for your dedication to the class. Please expect some emails maybe tomorrow or on Tuesday with materials from previous years. And there is a little homework that you may enjoy of making the Eigenstates. But main task is to prepare presentations for the first week. I will cover whatever is not covered towards presentations on Wednesday night and Wednesday evening. And on Wednesday night, midnight, I'm asking you to send me the PowerPoints so that we have them uploaded here next Thursday and they go seamless. Okay, thank you. Have a nice weekend. I'll stay here and answer any questions.
Not about this lecture. Through this course, we really go to learn VASP, VASP.
Yes, absolutely.
What's the pronunciation? VASP or VASP? What's common?
It's Vienna ab initio simulation temperature.
Okay. So we use this software for the projects?
We will use VASP for the projects.
Thank you.
How would it?